How are you all doing this morning?
Good.
All right, today we are going to talk about transient analysis of RL circuits. So what transient analysis is analysis of a circuit during a time of transition. So let me kind of explain what I mean by that. Let's say that we have the following circuit. It contains a switch, okay? This switch, as I have drawn it, is opening at a specific point in time, and opening that 5 amp current source to be removed from the 2 Henry inductor and the 5 ohm resistor on the right hand side of the circuit. So immediately prior to that switch being open, this is a simple DC circuit, and our analysis techniques that we've learned to this point are perfectly reasonable, right? So what I am saying is that if we plotted specifically our inductor current as a function of time, so here's IL of t, here is t, up until t is equal to 0, it should be trivial to determine that our inductor current has a constant value of 5 amps flowing through it, right? The inductor in a DC circuit behaves like a short circuit, so we would have a 5 amp source in parallel with a short circuit in parallel with 2 resistors, so obviously all 5 amps of the current being supplied by the source will flow through the inductor. At t is equal to 0, that switch opens up, right? And so what is going to happen is that all of the energy that is stored by that inductor will slowly be converted into heat by that 5 ohm resistor. Eventually, all of the energy that was stored in the inductor will be transferred to the resistor. And so at some significantly later moment in time, and I'm going to call this time infinity, but we'll find out that it really doesn't take nearly that long to happen. All of the, after this point in time, infinity, all of the energy stored by the inductor has been transferred into heat. And this time in the middle, between 0 and infinity, is what is called the transient So our circuit is going from DC steady state over here on the left our transient condition occurs, and then we achieve DC steady state again. Over here on the right. So now it's our job to figure out exactly what the heck is happening. Mr. Menendez, could you please mute yourself? Thank you. So what we are going to do is we're going to analyze a generic circuit during the transient condition specifically. Okay, so I'm going to redraw this original circuit that we're looking at, but we're going to look at things from a very generic perspective that we can then apply to literally any other circuit containing a resistor connected to an inductor. Here's an inductor. Here is a resistor. Sorry, actually, I want my switch to be opening, not closing. At t is equal to 0. And let's define my inductor current IL of t in this direction such that my voltage VL of t has this particular polarity. All right. So immediately after the switch has opened, we can write a Kirchhoff's voltage law equation for this simple loop here. So let's call this guy VR of t with this polarity. And we're following this current IL of t around its loop. So we would see the positive polarity terminal of VL first. So we have VL of t plus VR of t is equal to 0 based on the polarity of the voltages that I've given. And we can express both of those voltages in terms of that common current IL of t that's flowing around in that loop. Again, this is all happening after the switch is opened. So VL of t is going to look like L DIL by dt, and VR of t is going to look like R times IL of t. This equation is what's known as a first order homogeneous differential equation. So let me ask you guys a question. How many of you have taken Math 245 and learned about solving differential equations?
I've taken it already.
All right, a couple of people have taken it already. So for those of you that have taken it here, we are looking for a function in time where we can add the function itself and its derivative together and wind up getting an answer of 0. So what kind of mathematical expression behaves in that way?
You're asking like how to solve that equation you have right there, or like I was kind of confused.
Yeah, so okay, so what we are doing is we are trying to solve this guy. We're trying to form some sort of general solution for this guy, okay? One good thing, and I'll go ahead and let you guys know this, once we do this calculus here once, we will literally never have to do it again because all RL circuits will behave this way, okay? So as I said a moment ago, we are looking for a function where I have some constant multiplied by the derivative plus some different constant multiplied by the function itself. And when I combine those two terms together, they absolutely have to equal 0, because if they don't equal 0, then Kirchhoff's voltage law isn't being satisfied, which means the law of conservation of energy isn't being satisfied. So I want a function whose the function itself and its first derivative could potentially add together to equal 0. Any thoughts?
Exponential function.
An exponential function, okay? So let's make an educated guess here. I'm going to say that I believe IL of t will be of the following form. A e to the st. So it's a current, which will have some initial value, A, and it will exponentially either increase or decay, depending on what the value of S is, as time progresses. So if we substitute that guess value, okay, there's a question, why are we only looking at L and R? Why aren't we including the 10 ohm resistor? Okay, so fantastic question. Let me explain this explicitly. We are looking at the behavior of L and R during the transient condition, which means the time after that switch has opened up, effectively disconnecting that DC current source and that 10 ohm resistor from our inductor L and our resistor R. So let me move this math stuff down here. For now, and let me write explicitly. So for t greater than 0 plus. What I mean by that is the instant after the switch is opened, our circuit looks like this. So when that switch is opened up, it creates an open circuit disconnecting the the independent current source from influencing the behavior of what's going on with that inductor L and that resistor R. So under those specific conditions during the transient after the switch has opened up, if we apply Kirchhoff's voltage law around this loop, we will come up with this first order differential equation. Did that explanation of why we're only looking at the L and the R make sense? Not a problem at all. So what we're going to do is we are going to look at this guess value and substitute it into our differential equation, right? So that means that we would have L times the derivative of A e to the st plus R times A e to the st is equal to 0. So how do I take the derivative of that exponential function?
You just multiply by the exponent 5, and you multiply a, you raise e to the 5t again.
So, okay, so that's not a, maybe I'll draw this better. That's not supposed to be a 5, it's supposed to be an s, like we know what value it has, so it's another variable. But you're correct, we'll just take the derivative of the argument of the exponent, which is just going to be s. So this should look like s L A e to the st, and then we'll have R times A e to the st is equal to 0. So there's a common factor of A in both terms. Then I could have R plus SL, and there's a common factor of e to the st in both terms. And all of this must be equal to 0. So let's talk about the different ways in which this equation could be set equal to 0. So the first way is if A happens to be 0, okay? So that is what's known as a trivial solution. So if A is equal to 0, what that really implies is that everything is 0, which means our inductor never had any energy stored in it to begin with. So that would only be valid under the condition that IS, our source current, were 0 for all time. So while that is a solution, it really doesn't provide us with any information whatsoever, because it makes sense that if the current starts at 0 and we know after some long amount of time it ends at 0, it was probably 0 at all points in between. So that isn't helpful. Our exponential portion, e to the st, can approach 0 if s is negative, but it'll never completely get there, right? So instead, what we're going to do is we're going to solve this little guy right here, which is called the characteristic equation. And say R plus SL is equal to 0. And this will tell us what specific values of S will force Kirchhoff's voltage law to be satisfied, okay? So I hope it's not anything wild here. It's a simple equation. I can see that S is going to have to be negative L over R to satisfy the equation on the left. Everybody follow my algebra there.
Would it be the other way around, or?
Yeah, actually, yes. I made a mistake. Thank you. Negative R over L. You're absolutely correct. I'm thinking about something else we're going to talk about in a couple of minutes. Thank you very much. So S is equal to negative R over L. So if we substitute that in, our guess value becomes a little bit more specific. A e to the negative R over L t. So the only thing that we don't know is this value of A. All right. So now let's talk about how we figure it out. We know that the current flowing through an inductor cannot change abruptly. And so what that means is that the current flowing through the inductor at t is equal to 0 minus the instant in time before the switch opened, and t is equal to 0 plus the instant in time immediately after the switch has opened. The inductor current has to be the same, because if it is not the same value, then we have transferred an infinite amount of energy in an infinitely small amount of time, and we have broken physics, okay? So, could we analyze this original circuit at t is less than 0 plus and figure out what the inductor current was at that time? So what I'm asking specifically is for t is less than 0 minus the moment before the switch opens, our circuit looks like this. Our switch is closed, so I'm replacing it with a short circuit. We are at DC steady state, so I'm replacing the inductor with a short circuit as well. And I want to know what IL at 0 minus is. Who can tell me what the answer is? Or how we'd go about solving it for it? The answer is IS. That's absolutely correct. IL at 0 minus is simply IS. So we could say in general, A will really just be whatever IL at 0 minus is. And then we also have that exponential term there. Because this constraint right here is forcing our inductor current to be continuous, all right? So let me scroll up here again and erase this guy right here. We know now that during the transient condition, we expect to see that our inductor current will decay exponentially. Where it will have a value of its current at t is equal to 0 minus, which we know to be 5 amps. And then it'll be multiplied by e to the negative r, 5 divided by L, to t amperes. So that mathematical expression exactly describes how the inductor behaves during the transient condition. And this analysis that we've done here, if you can even call it that, will be true for any and every RL circuit that we will ever deal with, where specifically the sources are being removed. Okay, so I'd like to look at an example problem here and guide you through the generic steps that you will take when analyzing RL circuits. Okay, so
Is it always going to be like when you make, I guess when you make that initial guess, is it always going to be that exponential function? Like, could it never be like a sine or a cosine function?
So a sine and a so that's a fantastic question. Could it ever be a sine function or a cosine function? So the derivative of, let's say that we had made a guess that it was going to be a sinusoidal response here, okay? Meaning that when we open that switch up, we are assuming for whatever reason that the result of opening that switch or would cause the current through the inductor to start oscillating as a sine function, okay? Nothing, it seems a little odd, but it does also seem like a reasonable guess. So that would mean in our differential equation, let me erase this guy right here. We would have L times the derivative of, let's say that we had A cosine omega t plus some phase angle theta plus R times the same A cosine theta is equal to 0. So if we do this math, we would have omega L A negative sine omega t plus theta plus R A cosine omega t plus theta is equal to 0. Are you okay with the math that I've done to this point?
Yeah.
All right, so how do I convert I need to either convert my sine function to a cosine or my cosine function to a sine. Do you have any idea how to do that?
Not a single clue.
Okay, so in 4 or 5 lectures, we are literally going to learn how to do that, but I will tell you explicitly that sine and cosine are related there, and you can convert between the two of them just by phase shifting by 90 degrees. And so what I mean by that is that we could say negative omega LA sine omega t is the same as cosine omega t plus our angle theta plus an additional phase angle of 90 degrees. And then we would have R times A cosine omega t plus theta over here. So my question is now,
How can you shift one without the other?
okay, we're getting a little bit ahead of ourselves here, but I will absolutely explain.
Okay.
So I'm not actually shifting anything. What I'm doing is looking at it from a slightly different perspective. And so let me explain what I mean by that. Let's say that I have this graph where I'm looking at a voltage signal as a function of time. Okay, so let's say arbitrarily that my voltage signal is a sine or a cosine function, meaning it's going to start at its maximum value at t is equal to 0, and then it's going to decay to 0 in 1/4 of a period. It's going to go down to negative its maximum value after exactly 1/2 of a period. Then it's going to cycle back up to 0, and that total transition time takes 3/4 of a period. then it's going to be back up to its maximum value again, where this time between the positive peaks is known as the period of the cosine function, right?
Correct.
And it's just going to continue oscillating like that. So we would describe this function as, and let's call this guy V naught here. V of t is equal to V naught cosine omega t, where omega is equal to 2 pi times the linear frequency, which is then simply 2 pi divided by the period. And I want to make sure that that looks like a capital T and not a tau. Okay, so linear frequency you guys learned about in engineering 121. It's effectively how long, so the period is how long it takes for one cycle to occur. The linear frequency F is then the number of cycles that occur per second. And omega is the angular frequency, and it just tells us how many radians occur per a fixed amount of time. All right, so because we see that its maximum value occurs at t is equal to 0, we are arbitrarily calling this a cosine function. But if I draw another quarter period here, we could just as easily say that it is a sine function omega t that's been shifted by exactly 1/4 of a period, or 90 degrees. So what I mean by that is if we evaluate this so let's say that we have cosine omega t here and sine omega t plus 90 degrees here. I'm going to make a table here. So when omega t is equal to 0, what is cosine of omega t? Or what is cosine of 0?
1.
1. All right. What is sine of 0 plus 90? So what is the sine of 90 degrees?
1.
All right. Now let's say that omega t is equal to 90 degrees. What's the cosine of 90 degrees?
0.
What is the sine of 90 degrees plus 90 degrees? So the sine of 180 degrees.
0.
All right, now let's say that omega t is equal to 180 degrees. What is the cosine of 180 degrees?
-1.
Or -1.
Yeah. And what is the sine of 270 degrees?
-1.
And finally, omega t is equal to 270 degrees. This would look like 0, and this guy would also look like 0. So I'm not actually shifting anything. I am expressing that cosine function, or excuse me, what I'm doing is expressing that sine function as a exactly identical cosine function by changing the phase angle. So it's really just the exact same function, but we're looking at it in a slightly different way. So that's why I believe you called shift one and not the other. We're not shifting anything. We're just looking at the sine function as if it's a cosine function. Does that make sense at all?
Yes, sir, it does.
Okay, great. No, a fantastic question, legitimately. So now back to, I don't remember if it was Mr. Austin or Mr. Gray asking the question, but why we can't use a sine or a cosine function as our guess. what value of time well, actually, no. So let me think of how to ask this question correctly. Is there any way that we could add these guys together and have them equal to 0? So I have cosine omega t plus some phase angle plus 90 degrees multiplied by some factor or whatever. And then I have just cosine of omega t plus phi. Is there any way I can add those two guys up? And the answer will be 0.
Don't think so.
No. That's why sine and cosine can't be a guess for this first order differential equation. Now, when we get to second order differential equations, which we won't do in this class, but we will get to in circuits 2, it is possible for sine and cosine to work out under very specific conditions because we're dealing with a second derivative based relationship, right? So effectively, what that means is that when we take the second derivative, we're going to wind up, if we took the second derivative of this guy, we'd wind back up with a cosine function that has that phase angle theta on one term and a cosine function with that exact same phase angle theta on the other term, and those could potentially be combined to equal 0. But this first derivative based relationship, it will never work out. It's always going to be the exponential. So we will observe that for our first order differential equation based systems, so RL circuits and we'll see RC circuits come Thursday, they're all going to behave generally like this. We start at DC steady state. We remove our steady state condition. So our switch opens or our switch changes position. The circuit enters a transient condition, and we should observe either exponential decay when we're taking a independent source out, or exponential growth when we're adding an independent source in before we settle back to another DC steady state condition. All right, so I'd like to work simple example problem here. Sorry, give me just a moment to find it in my notes. So let's say that I have a 10-volt source an 8-ohm resistor, a switch that is going to open at t is equal to 0, and then a 4-ohm resistor here, and a 1/2 Henry inductor. And I want to know what my inductor current IL of t is for all t, and I also want to figure out what my resistor voltage is. So to be clear here, we're going to figure out I of t for all values of t, and we're, IL of t, and we're going to figure out VR of t for all values of t. Okay? So we are going to effectively do no calculus whatsoever, all right? Because we know that our inductor current has to behave in that general form I L of t will be equal to I L at 0 e to the minus r over lt, and this will be valid for all t greater than or equal to 0 plus. All of our RL circuits have to behave this way, or the law of conservation of energy is being violated. Okay? So, our first step will be to analyze this circuit at t is equal to 0 minus. Okay. So at t is equal to 0 minus, our switch is still closed, and so our circuit is going to look like this. We have our 10 volt source. We have our 8 ohm resistor. Our switch looks like a short circuit. Then I have my 4 ohm resistor over which there could be some voltage VR at 0 minus, and I will figure out what that is. And then I have my inductor, which, because we are at DC steady state before our switch is opened up, we're going to replace the inductor with its DC equivalent, which is a short circuit. Okay, right? We know that if the current flowing through the inductor doesn't change, then the voltage drop across the inductor has to be 0, which is exactly described by a short circuit. So, how could I determine either of these two quantities, VR at 0 minus or IL at 0 minus?
Use voltage division for the VR and then just regular ohms law with the 10 volt and 8 ohm for the IL.
So I understand your logic for wanting to apply voltage division, but there's a little bit of a problem, okay? So the first problem is that the 4 ohm resistor is in parallel with the short circuit, right? So we can't directly apply voltage division. We would have to combine the resistance of the 4 ohm resistor with the parallel resistance of 0 ohms caused by the short circuit. And so what that's going to give us is 0 volts. That's absolutely correct. 0 volts is right. But we could observe that by inspection because we know by definition that the voltage drop across a short circuit has to be 0 volts. So effectively, I'm saying that this voltage, which is the voltage drop over the inductor at t is equal to 0 minus, must be 0 volts because we are treating the inductor as a short circuit. And because the resistor, the 4 ohm resistor is in parallel with that, then the voltage drop over the 4 ohm resistor must also be 0 volts. Does that make sense?
Yes, that makes sense.
Okay. So we have the voltage solved for. How would we determine the current, IL? So if the voltage drop across the 4 ohm resistor is 0 volts, how much current is flowing through the 4 ohm resistor?
Would it be just no current flowing through it?
Right, 0 amps. Ohm's law tells us that if the voltage drop is 0 volts, the voltage drop across a resistor is 0 volts, then the current flowing through the resistor has to be 0 amps. So
Would you just find the current flowing through that 8 ohm resistor, and then that would be the current IL?
exactly right. So this current flowing through the 8 ohm resistor has to be the same as the current flowing through the inductor, because we know that none of it can branch off and flow down through the 4 ohm resistor. So how do I determine the current flowing through the 8 ohm resistor?
Just 10 divided by 8, and that gives you the current.
That's exactly right. 10 volts over 8 ohms. So that's right. Ten over 8 is 5/4 is 1.25. Yeah. So we have successfully analyzed this circuit at t is equal to 0 minus. Are there any questions whatsoever about the analysis steps that we took here? All right. Our next step will be to analyze the circuit at t is equal to 0 plus. So this is the instant in time after the switch has opened. So our 10 volt source still be over here doing its thing. We'll have our 8 ohm resistor right here. There will be an open circuit. Then here we have our 4 ohm resistor over which some voltage VR of 0 plus may occur. And out here, we are no longer at DC steady state, so we can no longer treat our inductor as if it were a short circuit. So for now, I'm going to draw it as an inductor having a value of 1/2 of a Henry, if I'm not mistaken. And here is our inductor current IL at 0 plus. And we need to determine those two quantities, VR at 0 plus. Does anybody have any thoughts on what either of these might be? All right, so what do we know about the behavior of an inductor? The inductor current cannot change abruptly. So what that means is that whatever the inductor current was at t is equal to 0 minus has to be what the inductor current is at t is equal to 0 plus. So this guy right here absolutely has to be 1.25 amps. Okay, if it is not 1.25 amps, then we are violating Kirchhoff's voltage law. So if we know that that current is 1.25 amps, I can actually redraw this circuit in a slightly different way that makes it easier, in my opinion, to determine what that unknown voltage VR at 0 plus is. So my 10 volt source doesn't change. My 8 ohm resistor doesn't change. My 4 ohm resistor doesn't change, over which that voltage VR of 0 plus, which is what we're interested in, is. But I'm going to represent my inductor a little bit differently. And so I'm going to explain why I'm doing it. So I'm going to represent my inductor with a independent current source, okay? The current will have the same direction as my inductor current, and it will also have the same magnitude. The reason why I can do this is because I'm analyzing the circuit at one instant in time. The instant t is equal to 0 plus, where the switch has just changed positions. And at this one instant in time, I know for a fact that the amount of current flowing through the inductor has a very specific value, and the voltage drop across the inductor will be whatever it happens to need to be, which is exactly how we could describe the behavior of an independent current source. So replacing my inductor with a current source at t is equal to 0 plus is a very common technique used to aid in these circuit analysis. So under that constraint, how would we determine that voltage VR at 0 plus?
Would VR not just be that 1.25 amps times 4 ohms? Because like you have a short circuit right there, or an open circuit right there, so you can't have any current flowing through it. So that 1.25 amps has to travel through that 4 ohms, correct?
You're
Or-
absolutely correct. The only slight mistake you've made here is that the current is flowing into the negative polarity terminal. And so therefore it would be negative 1.25 amps times 4 ohms, or so negative, gosh, that was not what was supposed to happen. 1.25 amps times 4 ohms looks like negative 10 volts. All right, so now we're actually ready to solve this guy. Step 3 will just be put our answers into the formula. All right. And so what I mean by this, so let me write something out here. IL of t will be IL at 0 minus for all t less than 0 minus. So that is the result of our analysis at t is less than 0 minus, okay? So what's going on before our switch opened up. And then based on what we learned earlier in class today, we'll have IL at 0 minus, or really IL at 0 plus, e to the negative r over L times t for t greater than 0 plus. Our inductor current, I cannot emphasize this enough, will always behave exactly like this in any system where we're removing independent sources from influencing the inductor. All right. So with that in mind, what was IL at 0 minus?
1.25 amps.
1.25 amps. All right. And then we'll put that same thing, 1.25 E. So what's R over L going to be?
Should it just be 4 over 0.5? That resistance 4 ohms over the
Right. So 4 over
What happened?
0.5 would be 8. Right. 4 divided by a half is 8. So this is what our inductor current will behave like. how can we use this to figure out how our resistor behaved? Okay, so let's look at VR of t, okay? We know that for all t less than 0 minus, it had a voltage of 0 volts over it, right? We proved that here when we did this analysis. How is it going to behave after the switch opens up? Anybody have any idea?
Would it just be 10 volts? Or is it like, going with 10 volts is my answer.
Okay, you're going with 10 volts as your answer. All right, so we know that at exactly t is equal to 0 plus, the answer is negative 10 volts because we discussed that. So my question to you guys is, let me draw this circuit again one last time. All right, so in this time, we'll be saying for all t greater than 0 plus. Okay, so we're not specifically looking at it at 0, we're looking at it for 0 plus and everything beyond. So we have our 10 volt source connected to our 8 ohm resistor. Then over here, we have our 4 ohm resistor over which the voltage VR of t occurs. Here we have our 1/2 of a Henry inductor through which a current IL of t is flowing. Right? This is our circuit for t, that's true for all time greater than 0 plus. So when we analyze the circuit at t is equal to 0 plus, you correctly deduced that all of that current IL of t is the current that winds up flowing up through the resistor. And it just winds up circulating around and around and around in this loop. So if that's true at t is equal to 0 plus, how is it not true for all t greater than 0 plus? That same current is just going to flow round and round and round, right? So our voltage VR of t at for t greater than 0 plus is just going to be 4 ohms, negative 4 ohms times IL of t, which I could say then would be negative 10 e to the minus 8t volts for t greater than 0 plus. Does that logic make sense? If in order for Kirchhoff's current law and Kirchhoff's voltage law for that matter to be satisfied, our voltage VR of t has to have the same exact form as our current. Meaning that our voltage needs to exponentially decay as well. If the voltage doesn't exponentially decay, and we try to apply Kirchhoff's voltage law and or Kirchhoff's current law, we would see that it breaks down. So what I am meaning by this, generally for any RL circuit, y of t which could represent a voltage or a current, will be of the form y at 0 minus for all t less than 0 minus, and it'll be y at 0 plus times e to the negative r over lt for all t greater than 0 plus, where again, y is any current in our system and any voltage in our system. I need to be away from my my computer for about 3 or 4 more minutes. So I'll be back as soon as I can. You guys feel free to discuss this stuff against yourself. We're going to work some more problems when I return.
So how's everybody's day going?
It's going okay, although I'm really confused in this and I've been confused since the second day, but it's fine.
All right, so let's look at another problem. Let's say that I have a 12-volt source that I am disconnecting from the following network. And I am explicitly trying to find my inductor current, IL of t. And I am going to be trying to find, let's say, my inductor voltage, VL of t. Okay. We're going to apply the exact same analysis steps that we did a moment ago And again, we're going to wind up using our general expression to get our values. And then we can actually use our calculus-based relationships to verify things if we were so inclined. So if I analyze the circuit, at t is equal to 0 minus, what this guy is going to look like is my 12-volt source, like so, connected to my 5-ohm resistor, connected to my 10-ohm resistor, connected to my 15-ohm resistor. Here's my current IL at 0 minus. Here's my voltage VL at 0 minus. How could I determine either of these quantities? So IL at 0 minus or VL at 0 minus. Anybody have any thoughts? On either of those two quantities. All right, nobody's saying anything, so I'm going to pick on somebody at random from the participant list. Kevin Cobb, are you paying attention?
I believe so.
All righty. What is the voltage drop over a short circuit?
0.
So VL is 0 volts. Do you agree or disagree?
Well, wouldn't it be the same as the voltage drop over the 5-ohm resistor?
It would not, because the positive polarity terminal of the inductor is here. The negative polarity terminal of the inductor is here, right? So we're looking at the voltage drop over the short circuit. If we were trying to find the voltage drop over the 5-ohm, sorry, this should be a 15, we would need to be looking at this node, which is not what we're looking for. Does that make sense?
Okay.
Yeah. So the voltage drop over an inductor at t is equal to 0 minus will always be 0 volts. It literally can't not be that. Okay.
Okay.
So thank you for your help there. Now let's talk about how we could figure out that inductor current IL at 0 naught. So the current flowing through the inductor at t is equal to 0 minus will be the current flowing through the 15-ohm resistor. So how could we figure out what that is? Anyone? So to be clear here, we have a circuit that contains a DC voltage source and 3 resistors to find the current through one of those 3 resistors. We are 17 lectures into circuits, and none of you appear to have any idea.
Could you find the voltage across the 15 ohm resistor and then do voltage divided by resistance?
Sure, so we could do that. So we could find the voltage drop across the 15 ohm resistor and then use Ohm's law to find the current. That would be a perfectly acceptable methodology here. How would you go about finding the voltage drop over the 15 ohm resistor?
Could you do voltage division?
Okay, so we can do voltage division. So I'm going to call this voltage right here VR. That is the voltage drop across the 10 ohm resistor, and it's the voltage drop across the 15 ohm resistor because they're connected in parallel. Hopefully that's obvious to everybody. So using voltage division, VR would be 12 volts multiplied by 15 ohms times 10 ohms over 15 ohms plus 10 ohms. So that's the equivalent resistance that I'm looking for the voltage drop over, divided by the total series resistance seen by the voltage source, which would be 5 ohms times 15 ohms times 10 ohms over 15 ohms plus 10 ohms. So let's see, 150 divided by 25 looks like 6. So that's 12 volts times 6 ohms over 11 ohms. $72 over 11 volts. And so from that, IL at 0 minus is equal to VR over 15 ohms. Looks like 24 over 55 amps. Or 0.436 amps. All right. Any questions about the circuit analysis steps that we took there? All right, moving on. We're going to analyze the circuit at t is equal to 0 plus now. So in this case, we still have our 12 volt source, but our switch is an open circuit. So here's our 5 ohm resistor. Here is our 10 ohm resistor. Here's our 15 ohm resistor. And just like I did in the last example problem, I know that IL at 0 plus must continue to be 0.436 amps because the current through the inductor cannot change abruptly. I'm going to replace my inductor with a current source that carries 0.436 amps. And now I need to figure out what this voltage VL at 0 minus is. Does anyone have any idea how we might, excuse me, 0 plus?
Sorry.
Yeah, no, thank you. So does anybody know how we might determine that voltage?
We're trying to find the voltage over like VL right there. So would you not just do the current through it multiplied by the REQ of that 10 ohm and 15 ohm since hold on.
You're close, you're very close. So let's call this guy V15. this guy V10, right? So it should be pretty easy to see that VL at 0 plus is just V15 plus V10 using Kirchhoff's voltage law. Does anybody have any problems with that statement?
No.
All right. So Sarah, since you piped up, I'm going to pick on you. How do I determine V15 and or V10?
Well, isn't it because they're in a series, they should have the same current flowing through them? So if you're determining the V15 or the V10, you would just use Ohm's law with the resistance that's given and the current that we found?
Absolutely correct.
Fuck
So
yeah, let's go.
we'll have the 15 ohm resistor in series with the 10 ohm resistor. So I'm just going to lump those guys together. Our current of 0.436 amps is flowing through both of them. So you're absolutely correct there. The only thing that I have to take into account here is that that current is going to flow into the negative
Oh.
polarity terminal.
It's negative.
Yep. And so now let's do that math. So effectively, I just answer or multiply my previous answer by a factor of negative 25. And I get an inductor voltage of negative 10.909 volts. So step 3, put stuff into our equation. We know that our inductor current IL, as a function of time, will generally be of the form IL at 0 minus for t less than 0 minus, and it will be of the form IL at 0 plus e to the minus r over L times t for t greater than 0 plus. So what was IL at 0 minus?
Like 436.
Yeah, 0.436.
0.436 amps. Okay. Then we're going to have 0.436 amps E. All right. So we got a little bit of a pickle here. The resistance that we put into our equation here be? Does anybody have any ideas?
Would it just be e to the negative 125 t? Because that's the 10 ohm plus the 15 ohms, that's 25 over 1/5.
Okay, so you are saying that the resistor that we should use is the 10 ohms in series with the 15 ohms. You're absolutely correct, okay? So from the perspective of the inductor, during the transient condition, it sees an equivalent resistance of 25 ohms. So it should be e to the negative 25 divided by, what was it, 1/5? 0.2t, so 25 over 0.2, 125, exactly what you said. So that's perfectly correct. Negative 125 t amps for t greater than 0 plus. Now let's look at our inductor voltage. VL of t will have that same general form. VL at 0 minus for t less than 0 minus, and VL 0 plus e to the minus r over L t for t greater than 0 plus. So That's going to look like 0 volts for t less than 0 minus, and it's going to look like negative 10.909 e to the minus 125 t volts for t greater than or equal to 0 plus. So I'd like for us to check our answer. Okay. We know that the voltage drop over our inductor is L times the derivative of our inductor current with respect to time. So for t is equal, for t greater than 0 plus, this is going to look like 0.2. Let's see, Henry's is volt second per amp, excuse me. Times the derivative of 0.436 e to the minus amps. That's going to be 0.2 volts second per amp times 0.436 amps times negative 125 per second e to the negative 125 t. So let's multiply these numbers together. So 0.2 times 0.436 times negative 125 gives me negative 10.909 e to the minus 125 t. Seconds cancels here, amps cancels here, volts. So even though we didn't once use our calculus-based relationship in analyzing this circuit, we still got the exactly correct expected answer using our fundamental knowledge of how the current and voltage characteristics of an inductor are related, okay? This methodology of analyzing the circuit at t is equal to 0 minus, analyzing the circuit at t is equal to 0 plus, and then just plugging stuff into a generic equation is literally the quickest and easiest way to analyze any of these circuits. So let's look at one last example problem, and then I will be done harassing you with math. Was there
Could you go back and explain the R real quick, how we got our R?
Absolutely. So this is the first circuit that we have dealt with where there were multiple resistors in place, okay? So I'm actually gonna go through how we find the R in general here, all right? Okay, so in our particular circuit, we had a 12 volt source. We had our 5 ohm resistor. We had our 10 ohm resistor. And then we had our 15 ohm resistor like so. And it's connected to our 1/5 of a Henry inductor. So this is what our circuit looks like during the transient condition, right? So for all points in time after our switch has opened up, this is what our circuit looks like, okay? So what we are doing is we are really just trying to find the Thevenin equivalent resistance as seen by our inductor, All right. So does anybody recall how to find the Thevenin equivalent resistance as seen by a circuit element? All right, not a problem. So whenever we are trying to find the Thevenin equivalent resistance directly, we need to be looking at a dead network, which means all of our independent sources need to be turned off. So how do I turn off a voltage source?
Yeah, short circuit.
Short circuit.
Short circuit. All right, so there's my short circuit representing my off voltage source. Now I'm going to just draw all my resistances. All right, so when I am trying to find the equivalent or the Thevenin equivalent resistance with respect to a particular circuit element, what I do is I take that circuit element out of our circuit and I look in through the terminals that are left behind. So this will be RTH as seen by the 1/5 of a Henry inductor. We remove the inductor from the circuit, look in through its terminals, and figure out what resistance we see. So what resistance do we see from the perspective of the inductor?
Ten ohms in parallel, or 10 ohms in series with 15 ohms.
Exactly right. Did that help explain where that equivalent resistance value came from?
Yes, sir. I was just wondering why like the 5 ohm wasn't in there, but I see it now.
Yeah, so not a problem whatsoever. This portion is not intuitively obvious by any stretch of the imagination, so some explanation there absolutely seemed appropriate. Let's, like I said, let's work one more problem where we'll use this methodology to determine the equivalent resistance again and put this into more practice, okay? So let's say that we have the following circuit. Where we have a 10 milliamp source is connected to a 5 kilo ohm resistor. We have a switch which will be opening up at t is equal to 0. Then we have a 6 kilo ohm resistor here. A 3 kilo ohm resistor here. A 25 millihenry inductor here. And a 2 kilo ohm resistor here. And our ultimate goal in this circuit is to find our inductor current, IL of t, and this resistor voltage, VR of t, having this particular polarity. All right, so we're going to do the exact same steps that we've been doing. Analyze circuit at t is equal to 0 minus. So in this case, that would be 10 milliamp source connected in parallel to our 5 kilo ohm resistor, connected in parallel to our 6 kilo ohm resistor. Then we have this 3 kilo ohm resistor over which we have a voltage VR of 0 minus. Our inductor is going to look like a short circuit because we're at DC steady state, where the current flowing through that short circuit is IL at 0 minus. And then out here, we have our 2 kilo ohm resistor. So we need to figure out what IL at 0 minus is and what VR at 0 minus is. Does anyone have any thoughts?
Could you do current division on the 3 kilo ohm resistor and then do to find the current flowing through the 3 kilo ohms and do that times 3 to get the voltage right there?
Okay, so that is absolutely a method that will work. But I want to point something out here, just because you're not making an assumption, but you've observed something that maybe not everybody else is going to observe, right? So that 2 kilo ohm resistor is in parallel with a short circuit, which means the 2 kilo ohm resistor isn't actually going to contribute anything to this guy whatsoever. So that, with that 2 kilo ohm resistor effectively thrown away, since it's not doing anything, we can easily see that the 3 kilo ohm resistor is in parallel with the 6 kilo ohm resistor, is in parallel with the 5 kilo ohm resistor, is in parallel with our 10 milliamp source, which is why we are able to do current division here, okay? So finding IL at 0 minus using current division is an absolutely wonderful way to get that particular value. So with that in mind, IL at 0 minus is going to be 10 milliamps. And then we're going to multiply that by, so we're going to have 1 over 3 kilo ohms in our numerator. And then we'll have 1 over 5 kilo ohms plus 1 over 6 kilo ohms plus 1 over 3 kilo ohms here in our denominator. And let me throw this into a calculator real quick. So I get 4.762 milliamps as my current IL at 0 minus. So before we move on to calculating that voltage, does anybody have any questions about how I applied current division to our circuit? Or are you all comfortable with that?
Pretty comfy.
Fantastic. So the suggestion was that our voltage drop across our resistor is simply going to be that current IL 0 minus times 3 kilo ohms. Again, we have to make sure that we are including the fact that the current is flowing into the negative polarity terminal. So we could say that VR at 0 minus is negative IL at 0 minus times 3 kilo ohms. Which would be negative 14.286 volts. Are there any questions regarding our circuit analysis at t is equal to 0 minus? All right. So our second step, as per usual, will be to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is an open circuit. And so what that gives us is our 10 milliamp source in parallel with our 5 kilo ohm resistor. And we have a big open circuit here. Our 6 kilo ohm resistor. Our 3 kilo ohm resistor, over which some voltage VR at 0 plus will occur. We're going to replace our inductor with a current source, so it has the same direction as our inductor current and also the same value, so 4.762 milliamps. And then out here, we will have that 2 kilo ohm resistor. We know that IL at 0 plus must be 4.762 milliamps because the current flowing through an inductor cannot change abruptly. So how do we go about solving for VR at 0 plus?
It'd be the current times the resistance, where the 6 kilo ohms is in series with the 3 kilo ohms, and then that's in parallel with the 2 kilo ohms at the end. Or
So finding that voltage is the current through the 3 kilo ohm resistor, which you correctly observe is also the current through the 6 kilo ohm resistor. I absolutely agree with that, but how do we find that current?
would it not be that 4.762 milliamps?
So why wouldn't some portion of the 4.762 milliamps split off and flow through the 2 kilo ohm resistor?
Oh, good point.
Could you use current division again?
We could use current division, absolutely. So I'm going to call this current right here IR. Okay, that's the current that's flowing through the 6 kilo ohm resistor and then also flowing through the 3 kilo ohm resistor. So applying current division, IR will be 4.762 milliamps multiplied by 1 over 6 kilo ohms plus 3 kilo ohms. Because remember, I have to take into account the total resistance of the branch here. So if this current splits and sees 6 in series with 3, then I need to put 6 in series with 3. Then that's going to be divided by 1 over 6 kilo ohms plus 3 kilo ohms plus 1 over 2 kilo ohms. So let's go ahead and throw that into our calculator. and I get 0.866 milliamps. And from this, VR at 0 plus must be negative IR, because the current is flowing into the negative polarity terminal, times 3 kiloohms, which gives me negative 2.597 volts. So now we are at the point where we're going to throw stuff into our generic equation. Assuming there are no questions regarding the circuit analysis that was done at t is equal to 0 plus. So before we do that, though, we're going to need to figure out what resistor value R we need to put into our generic equation. So we're going to approach this in the exact same way that I explained it for the last example problem. We are going to look at the dead network and we are going to take the inductor out, right? So our current source will look like an open circuit because that's how we turn a current source off. So here's our 5 kilo ohm resistor. We have our open circuit from the switch being open because we are doing all of this during the transient condition. Here's our 6 kilo ohm resistor. Here is our 3 kilo ohm resistor. Here's where our inductor was. So we're taking it out and we're looking in through this set of terminals. And then we also see over here our 2 kilo ohm resistor. So what should our Thevenin be?
Six in series with 3, and that in parallel with 2.
6 kilo ohms plus 3 kilo ohms in parallel with 2 kilo ohms. Absolutely correct. Does everybody else agree with that sentiment? If you don't
Yes, sir.
understand why it is, I'm happy to explain it. All right, nobody's saying much of anything, so that's going to look like 9 kilo ohms times 2 kilo ohms over 9 kilo ohms plus 2 kilo ohms is 18 over 11 kilo ohms. So now we're ready to rock and roll on our inductor current, IL of t. So IL at 0 was, 4.762 milliamps. T less than 0 minus, and then we'll have 4.762 e to the minus, so let's see, 18 over 11 kilo ohms divided by our inductor value, which was 25 millihenries. T greater than 0 plus, and I'm just going to do that math here real quick. 18 over 11 times 10 to the 3 divided by 25 times 10 to the minus 3. So this would be 4.762 milliamps for t less than 0 minus, and then 4.762 e to the minus 65,454 0.545 milliamps for t greater than 0 plus. So that current decays extraordinarily quickly. For our voltage, VR of t, the voltage at t is equal to 0 minus was negative 14.286. And the voltage at t is equal to 0 plus was negative 2.597. E to the minus that same thing, 65,454.545 t volts for t greater than 0 plus. All right, so let me ask you guys a question. How difficult did you feel that circuit analysis that we just did on this last problem was?
It wasn't too atrocious, but at the same time, you were also walking us through it. So,
Okay, so I posted some old exams the other day. I don't remember what day, but they're available under a section that says something like Exam 2 study material. If you looked through those old exams and you got to the transient analysis section, you would see that a circuit like this particular circuit exactly came from one of our tests, except that I just changed the direction of the switch because we're not quite where we need to be to discuss what happens when we add sources into things. It's not particularly difficult, but I just want to talk about that a little bit later. But anyway, on the transient analysis questions, or those circuit analysis problems, I literally walk you through it there as well. In as much as the first step of any of those problems is an individual question asking you to compute a quantity at t is equal to 0 minus. Then the next question is compute the quantity at t is equal to 0 plus. Then I ask you to calculate the time constant for the circuit. So we haven't gotten to the time constant just yet as a thing, but what we did right here is effectively calculating the time constant for the circuit minus one simple step. We'll cover that early on Thursday. So if the analysis that we did here in class today, this simple DC circuit analysis and then throwing things into the general equation makes sense to you, then congratulations, you're going to do pretty well on this next exam, because that's going to be roughly 40% of the test, legitimately. Our exam,
Joey.
yeah, our exam will be covering Thevenin and Norton equivalent circuits, which is practice inside of this. Then op amps, which will be like 2 to 3 questions tops. Then 2 to 3 on the inductor and capacitor material that we covered for the previous 2 classes. And then the remainder of the exam will literally be this transient analysis stuff. So if any of this isn't making sense to you, please look through some of my solutions that I have posted to the old test questions. And by all means, ask as many questions as you can think of during the next 2 lectures, because we're going to spend 2 more full class periods on transient analysis to make sure that you guys really get it. Okay. So if you have any questions for me right now, I'd be happy to answer them. I know class technically ends in 1 minute, but I don't mind staying on to help if you want some. If you don't need help, by all means, pop off the Zoom or whatever. But yeah, if you've got questions, I want to help you understand this stuff, because not only is it very important for this class, but it's also extremely important circuit analysis knowledge in general that can be applied to a variety of majors. You can use this transient analysis stuff to analyze fluid flow and heat transfer and all kinds of good stuff like that for majors besides electrical engineering.
I've got a question, like, does not relate to circuits literally at all.
Okay.
So we were on Zoom the other day, and I seen like you had a notification pop up, and it said your password will expire soon.
Yes.
Yeah, what does that mean? Because I've been getting the same notification, and it's my tech email.
Yeah, so it's okay. So I think that is I use my tech email address for my Windows account as well. So like how I log in and I'm able to use like the Office 365 suite and stuff like that. So Word, Excel, all that jazz. I think it's meaning that password is going to expire soon. That being said, I've been pressing ignore for the better part of, I think, 5 months at this point, and I'm still able to use all of those programs. So I'm just going to be lazy and not change my password until it forces me.
I was wondering because I've had to change my password, like my tech password, like a bunch of times, or like at least 3 times. I just didn't know.
I've been using the same Louisiana Tech email password since I was a undergraduate student. So like I've had the same password for both my student and my faculty email address for, at this point, probably close to 10 years.
It made me change my password. Like I think it was last summer. It made me change it because it wouldn't let me log into like Moodle or WebWork or anything at all.
Yeah, I think I'm grandfathered in for being on the old system, so I still use webmail, where I think that you guys are required to use the Google Mail and all that kind of crap now, right?
I use webmail too. I started in 2017, so I still use that. But I got some friends that they're using the Gmail something.
Yeah, all that Gmail stuff is annoying to me. Yeah, I have no idea why tech is forcing you. Maybe it's a recent thing and they're just making students do it. I don't know, but I've never been required to change my tech email, to my knowledge, in years and years and years at this point.
That's all I needed to know.
All right. Anything else, circuits or non-circuits related? All righty. Well, I will see you guys on Thursday, and we're going to look at the analysis of RC circuits, which will be extraordinarily similar. So see you guys Thursday morning.